Okay, let's okay. So I just started recording. We repeat, right? We learned everything about Maxwell equations. Okay, we start from integral form of Maxwell equations. Integral form of Maxwell equations. Then first, Faraday's law, the time varying magnetic field, the flux create electrical field, right? So either you see it doesn't change with time, but however the flux change with time, right? The total flux change with time. So this is a Faraday's law, and the Am's law is a time varying electrical field create magnetic field. Okay, so that means the magnetic field we have two sources. One is time varying electrical field. Okay, the time varying electrical field, and the second source is the current. This current you applied. Okay, this current can be DC, can be time invariant current or time varying current. Also both current create magnetic field. So magnetic field has two sources. Okay, and the very, very significant, the most significant contribution in Maxwell equations is this term. What is this? This is what we call displacement. Displacement current. This displacement current, okay, is not observed from experiment. It's from mathematical energy conservation. Okay, so in addition to these two equations, we have another two equations that describe the total flux of electrical field over a closed surface. This S is not closed, but this is a closed surface. Okay, because you can tell from integral form, right? This is not closed. Okay, not. Let me put this way. So, not closed surface. But this is closed. Okay. Right. So the electrical field, the total flux over closed surface, okay, equal to the total charge enclosed by the surface. This is what that says. Okay. And another important law is the total magnetic field goes through a closed surface always equal to 0. Okay. So this is what the integral form of Maxwell equations. So I also post an interesting article. Okay. So that tells you how this permittivity and the permeability is determined. Okay. In that associate electrical field flux density with electrical field intensity function, or magnetic field flux density, okay, with magnetic field intensity function. Why it is called flux density? You see, because here we calculate the flux, right? Then we calculate flux on D. This we also calculate the flux on D. This we also calculate the flux on D. So that's why we call B and D a flux density. And the other field, you see, these two fields related to the line integration, we call the field intensity. We are not calculating flux. Okay, so that is maybe the reason people call, one is called field intensity function, one is called flux density function. Right? And in addition to these four equations, don't forget we have another charge conservation, a current conservation law. Right? Then before we introducing differential form of Maxwell equations, we introduced the curl, okay, of a vector. Okay, this curl of a vector. So this is definition. Okay, the definition of vector, that is a first principle. We mentioned in Cartesian coordinate system is very straightforward. Okay, we can calculate the curl. Okay, and also you can calculate the curl in other coordinate system. Those formulas I won't use this and this in middle term. You don't need to write in your CAD paper. All right. Okay. Then from the curl equation, from the curl definition, we can justify what we call a Stokes theorem. Okay. The Stokes theorem means if you do a surface integration, okay, if you do a surface integration with, you see, to calculate the flux of a vector over a surface, okay, over a surface, if you can express this vector, okay, if you can express, say, if this is vector B, if this vector can be expressed in terms of curl of another vector, then the surface integration can be calculated by doing a line integration. So this is what we call a Stokes theorem. So after we introducing curl, we also introduce another. You see, we only have a 3 vector differential operators. Curl is one. Okay. The second one we call divergence. Okay. So divergence is defined by divergence of a vector field. It's defined by, I calculate the flux of this vector field first. Flux goes through a closed surface. Once you have a closed surface, you have a volume. Then I let the volume shrink to 0. And there's also this total flux, I divide by this volume. Okay. I let this volume approach to 0. This is our definition of divergence. When you shrink to 0, that means this is a property of a vector field at a particular point. That is in the center of this volume, right? Okay. So with this definition, we can also find another very important theorem we call divergence theorem. Okay. This divergence theorem says if you do a volume integration, if this integral can be expressed as a divergence of a vector, okay, then this 3-dimensional volume integration can be calculated by calculating a total flux of this vector. Okay. If this function f can be represented by a divergence of A, because divergence of a vector is a scalar function, right? Then this volume integration will become you're calculating this flux density. Okay, this flux density. If so, this is what the divergence theorem says. Okay, divergence theorem. Now the last you see another very useful vector identity we are using all the time is for any vector you calculate the curve. Okay, sure, any vector you can calculate curve. Then if you take a divergence of this curve, it's always equal to 0. Okay, this is a vector identity. So this vector identity applicable to any vector field. Okay, then using this vector identity, what we can do is later on we can justify the 4 Maxwell equations. Only 2 are independent. Okay, only 2 are independent. Okay, now let's say from the definition of curl, definition of divergence, and those divergence theorem, Stokes theorem, then that 4 integral form of Maxwell equation can lead to 4 differential equations. Okay, one by one. Okay, so this is Faraday's law, this is Am's law. Okay, and the other 2 divergence, one is for electrical field, and the divergence is the relation for magnetic field. Okay, and also you can justify if you take curl, take a divergence of this on both sides. Okay, then you can find these 2 equations. Of course, you have to use this. Okay, the last equation is also, we have integral form of, that is a current continuity equation. Okay, so those equations, we said only this, and this independent. Okay, other 2 divergence theorem, okay, the divergence equation can be derived from the 2 curl equations. So that's why you say in the following discussion, we only use the curl equation. We didn't use the divergence equation, okay, to find solutions for plane wave. Right? So far, you say, I suppose you say, if this is closed book exam, the Maxwell equations definitely is a question we will ask. Okay, so if you couldn't remember Maxwell equation, and then it is a failure. Okay, it is a failure. So for sure, Maxwell equations you need to write down into your CAD sheet. All right. Now we're talking about more practical use of Maxwell equations. The most simple solution of Maxwell equations in source free that means the field location doesn't have any source. The source is, what is source? We have 2 kinds of source. One is current, one is charge density so far, right? In source free region, that means equal to 0. Okay, no current, no charge distribution. Then we find a simple solution is we have electrical field. We have electrical field polarized in x direction. When we say polarized, that means the field has changed with time or not changed with time. We have, this is a vector, how this vector chases change with time, right? If change with time, sometimes positive, okay, then magnitude reduced, then, okay, so this is time. And then another time go opposite direction, okay? So this is always polarizing, either positive, negative, positive, negative. So this we call linearly polarized. right? And then also we have some field, okay, change with time. Okay, change with time, but rotate. Okay, maybe the magnitude is constant, so we call circularly polarized. Okay, we'll talk about this, briefly review it later on today. Right? So we discussed the plane wave. Is the plane wave, we have electrical field polarized in one direction, magnetic field polarized in another direction. However, electrical field and the magnetic field, they must perpendicular to each other. We justified this. All right, we don't reprove it. Okay, they must orthogonal to each other. So that means if this is a x direction, magnetic field must be in y direction or minus y direction. It depends on what is the direction of wave propagation. Okay, if E cross H, okay, E cross H, the thumb point to the direction of propagation. Then if magnetic field in minus y direction, then the wave propagate in minus z direction. Okay, so electric field and magnetic field has this difference. It means when the wave propagates in opposite direction, the sign for magnetic field is different, right? And how we found the specific field solution, we start from these two Curry equations, okay? And then we justified, right? We only have EX only, right? And the EY, EZ equal to 0. And in the same time, okay, then the variation in X direction, the variation in Y direction also 0. Okay, under those conditions, we can write the Maxwell equations in a very simple form. This is Maxwell equation, right? This is Maxwell equations in the conditions that of this, all right? Then we found, okay, the solution of such, under such condition, the EX field has a solution, magnetic field in Y direction also has a solution. The solution contains two components. One is arbitrary function with argument of this. And another function is with argument is t plus, the other one is t minus. Okay, this is t minus, this t plus. These two solutions represent waves propagating in two opposite directions. And also the ratio of EX over HY, this must be a constant. This constant, okay, this constant equal to this we define as eta 0. This is approximately equal to 120 pi, okay, which is a constant. Okay, then this is a very, very general form. Okay, very, very general form, because the two solutions F and G, we didn't give a specific form. Okay, we didn't, but we know that such solution exists. And the field we are interested in most is sinusoidally time varying field. Okay, that means the field, both F or function G, is in the form of cosine omega t, okay, cosine omega t, and plus or minus or plus beta z, okay, then plus another phi constant, okay, it's in this form, okay. In the form of cosine, right? And of course, sine is also a cosine. Let's say if this is sine phi, right? Always we can write as cosine phi minus pi over 2, right? Okay, always. So if I write as sine, it's same as cosine, right? The only difference is I have to add another phase offset, okay, phase offset. So therefore, because we are only interested in time varying field, sinusoidally time varying field, okay, then we are interested in the field is in this form. It's in this form, okay. Here is a cosine, okay. Then cosine omega t, which is function of t, right? And then minus plus beta, basically we have a minus sign, we have a plus sign, okay. So beta z, then from here, the beta is what? Is just this, right? Sorry, times omega, because this term, the cosine omega t minus c beta z, I can write as cosine, I take out omega t minus omega beta z, okay? If you compare this to f t minus z vp, then you see, if this is a function of t, omega t is also a function of t, right? So therefore, beta omega is in the same position as this, right? The same position. You compare these two. Okay, I don't have time to discuss more on this. So we can say this is exactly complying with our solution form. This is what I just said. Then we have X component. We have a magnetic field Y component. The plus minus sign depends on the propagation direction. And also the magnitude EX over HY exactly equal to this, okay, right? So this is our relation. This is, we should able to write it down where you close your eyes, right? And you see how this is determined. This magnitude is determined. I haven't mentioned yet. Actually, we mentioned because this is determined by the boundary condition. Okay, we will review it in the last slide today. So this is a time sinusoidally time varying magnetic field. Okay, then for this field expression, we define everything within the bracket as a phase. Okay, phase phi. Okay, you see, I write like a phase. This is a phase. Then how fast the phase change with time? Okay, that means I take a derivative of a phase with time. Then you can say, what is this? This is angular frequency, right? This is angular frequency. Then if we know the omega and the omega related with f is 2 pi times f equal to omega, right? So this is the omega is the angular frequency. And also, we like to say, if the how fast this phase changes with distance you travel, okay? first the phi with time, right? And then there's phi with z. If you take a directivity, partial phi, partial z, this is 0, right? Because it has nothing to do with that. And the last thing, this is equal to beta, okay? Equal to beta, or plus minus, equal to beta. So we have this we call a phase constant, and the omega is the angular frequency. Then, having had discussed this, is mean if we know beta, if we know omega, we can write down the solution. Okay, except we don't know that we have initial phase, we don't know, right? And also the magnitude. If I say the magnitude, so I don't know the magnitude, but however, you see, the magnitude can be determined by boundary condition. We had assignment, we had a problem in assignment 5. Okay, so if you have done assignment 5, you should understand how to determine this coefficient. And also I can tell you, we have a problem in middle term exam that related, that ask you to determine this magnitude constant. Okay, the magnitude constant using the given boundary condition, right? And the initial phase you have two reasons. You see, we have two ways we can determine it, right? Because the absolute phase reference is really not important. Okay, important is the phase difference is because of when you compare with another quantity, they have a phase shift. So this can be seen when we have a loss in the medium of wave propagation. In that case, the phase for magnetic field and the electrical field will be different. Okay, then we have a phase term. This is sinusoidal wave. Then we know how to determine phase velocity and also the phase constant. Then this is example we come from our notes, from our course notes. So what I just like to emphasize is for some problem, if we gave a frequency, so 100 megahertz, okay, see, this is 100 times hertz, okay? Then you know omega equals to 2 pi f, right? 2 pi f. No, you know this, right? And if people say if the z 1t equal to 0, 1t equal to 0, you already travel that much distance. That means that gives you a kind of indication you can determine the initial, you can determine the initial phase, right? You can determine initial phase. So why is this? Is because 1t equal to 0 give you a maximum value. When this reach to maximum value is when this the whole phase of cosine equal to 0. This reach to maximum magnitude, right? Then for giving this condition, you set t equal to 0, you set z equal to 1/8 meter. From this equation, you can find phi, right? Okay, obvious. This just gives you a condition that you to determine the initial phase, All right, so this is equation we set, right? This is initial phase. So already give you a maximum value, the frequency, give you a frequency. From this equation, you can determine the initial phase. Okay, you can determine the initial phase. And then you also from the velocity and also omega, you can determine beta, which is beta is always in front of variable z, right? Where's the beta? You see? Beta is a quantity in front of z. Then you have everything you can write down. You can write down the expression for electrical field. And don't forget, electrical field is a vector. Then you must have a polarization direction. Okay, so this is unit vector for polarization. Okay, this is for polarization. This is in x direction. And if you know electrical field, we can calculate intrinsic impedance, intrinsic wave impedance. Then we know magnetic field. Of course, in this case, we must know what direction is the wave propagation. Okay, then E cross H is a propagation direction. We just mentioned polarization direction. Polarization. So this is linear polarized. This is circular polarized. Okay. Then this is elliptic. That means the magnitude is not constant. Okay. Then we spend a lot of time discuss circular polarized wave, and we also said the very important application for circular polarized wave is satellite communication, GPS, right? GPS. And we were asked this question in midterm, so I already tell you many problems in midterm. Right? Then we specifically discuss if we have two plane wave, we call plane wave, right? Why it is called plane wave? Because the phase change with time is always z, or z equal to constant, right? Z is a propagation direction. We know the plane wave in instantaneous form, we can write the magnitude, okay, the three basic things. Three basic things: magnitude. This must be a cosine something, right? Okay, so must be a cosine something. Then frequency you must know, right? So the three things is magnitude, and this is a phase. Phase. Okay. One more thing. The polarization direction. Okay, polarization. So these three things, right? These three things. And then this is the big three things, okay? We can say big three. And then you can have a small three. Small three is omega, beta, phi 0. So this is a small tree, okay? We have a big tree, we have a small tree to completely describe one plane wave, okay? One plane wave. And let's assume we have two plane waves propagating together, okay? One polarized in X direction, one polarized in Y direction. They are all electrical field, okay? All electrical field. Same frequency, okay? Same frequency, but a different phase, okay? Because I rewrite this. I rewrite this as cosine omega t, right? So actually this, I omit one thing. This is not very accurate because we said we have a small three things, right? So we have a beta z is missing, okay? Minus beta z is missing, right? Okay, now I add this, okay? And I have phi, and I minus pi over 2, okay? Oh, forget. Three big things I have. Another is the polarization direction, okay? Polarization direction. Is that clear? I have two plane waves, okay? Because I emphasize circular polarized wave will be covered in middle term, right? Okay, to describe this, we have first, we have a sun magnitude, O F0, okay? Two components, okay? Two components, perpendicular, X and Y, right? And third thing is they have 90-degree phase difference, okay? Right now, I have, okay, I have 90-degree behind, okay, minus, okay, behind. Then we also justified for this wave, the polarization rotate, follow the right hand rule, okay, follow the right hand rule, right? And then how to determine this? Do you remember we had a table, right? We have EX component, we have EY component. Let's look at omega t, right? One z equal to 0, okay? Let's assume phi also equal to 0, okay? Then you said z equal to 0, phi equal to 0, 1 omega t, say equal to 0, and equal to pi over 2, and equal to pi. You just make a judgment of only for two rows. You can know how the vectors rotate, right? Okay. From this case, we can justify, we have three, right? We can justify satisfying these three things, okay? Sun magnitude, okay? Sun magnitude, two orthogonal component, okay? Then third one is plus minus pi over 2 phase difference. Okay, then we create a set of a circular polarized wave, okay? Circular polarized wave. Oh, so that's these three components here. And later on, we will introduce, okay, later on we will introduce, sorry, when your next tutorial start? When will your next tutorial start? Okay, 10:30. Then I will still, I will take 10 more minutes this class. Okay. Okay, we will revisit circular polarized wave today. Okay, after we review the phasor. Okay, we will come back again, right? Because this is we're still using sinusoidal functions, and it's not clear, not very clear, or not convenient to do analysis, right? Okay, now we introduce we call a powerful or energy conservation of electromagnetic waves. And this is a very famous, we call a pointing theory. Okay, what pointing theory says, okay, the E cross H has a very significant meaning, physical meaning. That stands for a power density. Stands for power density. Okay, this is a power density. Okay, this is power density. Then power density integration over closed surface, that means the net power go in and go out. Okay, it may not exactly equal to 0, depend on what do you have on the right hand side of this equation. If the right hand side equal to 0, then you have no power consumption, you have the stored energy, the balance. Okay, stored energy is balanced, right? But in multiple cases, this is not true, right? So we have this is real, always real. So that means as long as you have conductivity, okay, the medium is conductive, you have a loss. Okay, and the other two terms stand for the stored energy. The stored energy. So one is the stored electrical energy, one is stored magnetic energy. Right. So we can justify this. We derive this from Maxwell equations. Right. So that is one thing we introduce, and another is we call constitutive relation. The constitutive relation is the relation between H and B, and the relation between D and E, right? Between D and E. So the D is related to E with constant we call permittivity, and the absolute permittivity in free space, this is a constant, but this is not. This is we call relative permittivity, right? And the same as the B, we call the permeability. We have a relative permeability. We have a constant. Mu0 is always constant, right? So but for most of the material we are dealing with is not a magnetic type of material, and the relative mu_r is equal to 1. All right. Okay, we introduce very important concept, and this concept we have to deal with, and we use to deal with plane wave. Much more convenient. We call phasor. Just now we said, okay, this term in sinusoid form, we can write. We said we have a tree. We have a big tree and a small tree, right? Big tree, we have a magnitude. Okay, then there must be a cosine function. Okay, we have a phase. Okay, this is second. This is phase magnitude. And we have a polarization direction, right? Say polarization direction. But this is too much work, okay? Because this form itself can be written like this. Because if you multiply E j omega t, take a real part, which is this, okay? But however, this is not, okay. In order to write this, we have to reflect this part, because E j omega t only reflects to here. We have another part, right? And all this part together with this we can write like E0, okay, minus J okay, then this times J omega T, we take a real part. Okay, this equal to this. You agree? Okay, this equal to this. Then we define everything here. Everything here we call EX. We put a hat if you wish to make a difference from this. We call this term, we officially call this term called phasor. Phasor is not a phase, okay? Phase is always real, okay? Phasor is a complex number, okay? But a complex number has a phase, so it's very tangle trace, okay? All right, okay. Complex, we have a phase, we have magnitude, okay? But the phase itself is real, right? But the phasor, always a complex number, but not every complex number you can call a phasor, because a phasor is a specific term that associated to the sinusoid wave, or we call time harmonic wave, right? So after we introducing phasor, and in Maxwell equations, so we can determine this term as a phase constant, because this is in front of gamma is in front of z, right? Because this is solution of, this is a wave equation. I emphasize this wave equation is if you can justify your equation is in this form, this quantity must follow a wave property. And we have a similar question in middle term about wave equations, okay, about wave. So for the wave equations, you have two solutions. One is this propagating in that direction. One is this propagating in minus that direction, right? Then since the gamma obviously is a complex number, so I can write gamma into real part and imaginary part. And I just had a question before we start today is how to determine alpha and beta. Alpha and beta determine this. This is a very complex question. But however, if we only look at three special cases, one is lossless. Okay, that means the conductivity equal to 0. This is obvious. Alpha equal to 0, right? And the beta we already know. Beta is omega divided by phase velocity, right? Second case is a low loss. Okay, in that case, right, the sigma is not equal to 0, but compared to omega times epsilon is much, much smaller, right? And then we also discussed high loss. High loss case, for example, conductor, right? So if this is much larger than 1, in these three cases, we have discussed how to find alpha and beta, okay? So you can check your notes. Okay, then we have no time. So I give you 5 5 minutes to break and before you go attending your tutorial. Let's resume our review from 11:30. Okay, and Tansha, please send the room link to everybody. Okay, and post it, and also send me a copy. Right. Okay. So see you later. Okay, I just resume my recording. Let's continue the review of phasor, right? So phasor must be, a complex number. Right? You see, because we need to involve all the phase information of a wave. Okay, all the phase information of the wave, we should all incorporate it in the phasor. And the phasor and the instantaneous expression are a pair of transformation. Okay, so when we deal with the phasor, it's much convenient in deal with phase, right? But however, you say phasor is a kind of imaginary number. Okay, that's not measurable. Okay, not measurable. But however, you say the instantaneous field, that is a real number that can be measured. So the relation between the phasor and the instantaneous relation is this. This is how we define the phasor, right? This is how we define the phasor, because this is a phasor. Okay, this is a phasor, and this phasor, you can say specifically, this is phasor, right? Right. So this is something, right? This is a phasor, and when we convert a phasor into instantaneous relation, we need to multiply the phasor. We need to multiply the phasor by this ej omega t. This is a time convention. Okay, time convention for all engineering people. Okay, for all engineering. All right, okay. I will leave time for our student to ask question. Okay, let me quickly finish this part. Okay, so once we have this convention, or apply the time convention, we take a real part, we can convert into instantaneous. So this is a real number. Okay, this is a real number, right? Okay. So I like to draw a special attention. Okay, I like to draw special attention is this, because we are dealing with phasor. Okay, we're dealing with phasor. So in phasor, then also when we deal with lossy media. Okay, lossy media where we have a conductivity which is not zero, then the wave impedance will be also a complex number. So this complex number we can represent like in magnitude and the phase. This is a phase, because this is a complex number, right? Complex number in magnitude and the phase. Okay. Also, when we deal with plane wave, we know Ex over Hy, that equal to intrinsic wave impedance. And this is a complex number. Okay, this is a complex number. In another word, if we know electrical field, when we convert into magnetic field, okay, when we convert into magnetic field, how we convert into magnetic field is we take electrical field, okay, so in this case, electrical field, so electrical field is A and B, right? So we know electrical field propagating in positive z direction divided by intrinsic wave impedance plus the wave in reflect in opposite direction, but this time must be minus, okay, must be minus, also divided by intrinsic impedance. Oh, let me put this way. This is a plus minus. This is for wave positive z direction, minus z direction, positive minus z direction. So the ratio is different, okay, plus and minus. So in reflected wave, we have to take minus sign, right? So in this case, be careful, this is a complex number. When we convert into instantaneous expression, we have to be using complex number, and then this complex number, we have to convert this phase into imaginary part, okay, into imaginary part. You see, in this case, we convert this into the imaginary part. Now you see, where this come from? This comes from the phase in the denominator, okay, in the denominator. So we have a minus sign. And this is also, we have a minus sign because we have this move to the phase, okay, and leave the magnitude is the magnitude must be a pure real number, okay. You cannot take a real part without considering this complex number, okay. So this is what I want to say, okay. So this is about phasor and about a plane wave. And in plane wave expression, in terms of plane wave expression in terms of phase, we have three factors, okay. So this is a phasor x component, okay, x component, or the electrical field, okay. In phasor, what we have is we have a magnitude. This is magnitude, okay. We have a magnitude, we have phasor, okay. This is phasor, right? This is phase, okay. Then we have polarization. Then we have a polarization, okay. So we have these three things. We have these three things, right? And don't forget, we have another thing we have to keep in mind. We also have this. This is a part of the phase. This is part of the phase, right? So overall, the phase part, we have that determined by omega, by beta z plus phi plus omega t, okay. But this is imaginary, then I can put, negative, negative, and positive, okay. So this is phase. Phase, we have three factors: omega, beta, and initial phase, right? We have a big 3 and a small 3, right? So in phase. So now let's come back to circular polarized wave, okay? Circularly polarized wave also is more convenient to deal with circular polarized wave in terms of phasor. Okay, let's look at the first term. Let's look at first term. So we have first term, we have a magnitude, okay, and then cosine omega t, okay. Then let's suppose the wave propagate in positive z direction. So we have minus z, we have initial phase, okay. Then polarized, let's say, in x direction. We have one wave. We have another wave, okay. This wave, I also write it in cosine, okay, in terms of cosine, because that is the reference we measure the phase, right? That initial phase, this is this term, right? And this is sine, so this is minus pi over 2, okay? And this is polarized in y direction, okay? So this is instantaneous form. And okay, the phasor form. The phasor form, we also have a magnitude, okay, E1. This is a phasor form, okay? So we have magnitude, okay? So so far I just read in this way, okay? Then I have J phi. This is this, okay? Then I have okay, right? So then I have, all right, then this I read in this way, okay? Then what is a phasor expression if I keep this in, oh, sorry. If I keep this in mind, okay? Sorry, this is a beta z. This is beta z. Okay, then what that is, I can write F1, this is a phasor, okay? Then so this is a phasor 1 that equal to J beta z minus J beta z minus 5, okay? Minus 5, and with a magnitude, I see it. Okay, so this is a I can write in this form. Okay, similarly, F2. Okay, similarly, F2, the polarized in x direction. Okay, polarized. So F2, I can write as F2 polarized in y direction. So let's say what is F1? F1 equal to F0 E minus G plus G phi. All right, and F2 also some magnitude. In addition to this G phi, I have another thing, is because I have this minus pi over 2, right? This minus pi over 2, I can put in this way. Okay, this is a minus pi over 2. Or this equal to minus G F1. Okay, minus G F1. All right, so the total E field, this total E field, I have two terms. One is F1, the phasor propagate in that direction and polarize in X direction, and then minus G F1. Okay, so this one F1 I can then you say what is the essence for this right hand circularly polarized wave? Okay, this means we have something is, this is in common, some magnitude, okay? And then we have two polarization, okay? But however, we have minus G. The two component, the Y component has a minus G. So this is to reflect the minus 90-degree phase, right, in the Y component. Similarly, you can prove the left hand circularly polarized wave. I can write, this is E field, okay? I can write, if this is F1 plus G, so this become left hand circularly polarized wave. The only difference is the phase. This is 90 degrees behind, this is 90 degrees in advance, okay, between the two components, okay, the X and the Y component. So this is that make the difference of the two circularly polarized wave. And it is very important if the wave coming in right-hand side, right-hand circular polarized. If you use a left-hand circular polarized wave antenna, you cannot receive anything, right? This is the way we can judge circular polarized wave in terms of phasor expression. Okay, then very last page is of our review is the boundary condition. Okay, the boundary condition tells us the relationship between the field next to the common boundary of the two mediums. Okay, what I said is the tangential electrical field must be continuous. So the difference equal to 0. That means equal. Okay, the tangential electrical field. And the tangential magnetic field will be different. The tangential magnetic field, the difference will equal to the current between them. That the current is on the surface, the current. the tangential magnetic field, the difference between the two medium, the tangential field in medium 1 minus tangential field in medium 2 equal to the current, then the vector relation is the normal component of the surface from medium 2 point to the medium 1. Okay, this is a normal component. Cross multiplication of the tangential field difference that equal to the current. So that means the current direction is equal to the n cross the magnetic field in medium 1. All right. Okay. So that is the relationship of the tangential field across the boundary. The boundary condition for the normal component of electrical field, that is related to the charge density on the surface. A very special case is if one is conductor, perfect conductor, okay, then you have a normal component, then you have charge density, surface charge density on the conductor surface. So these were equal to the normal component on the surface of electrical field flux density. Okay, so that is how we measure the charge density. Okay, then for magnetic field, the normal component B should be continuous. Okay, and also we know the electrical field and the magnetic field inside perfect conductor is always equal to 0. Okay, always equal to 0. So that's why we have E tangent field on the boundary equal to 0 and the normal component equal to 0. Okay. So that is the review. Okay, what I proposed. I had some of the questions asked privately. Can you see, let's make more effective. We can slide 15. I don't know which slide. Okay, let's ask a question verbally. Okay. So I don't know, lesson 15, I have very difficult to come back to particular lessons. You can ask your question, what your question is. Okay, here already asked question. So any questions we can share?